All right. Excuse me. Good evening, everyone. It looks like good morning as well for some. I just want to make sure that you have got me loud and clear. If you could let me know in the comments, please. Just waiting here somewhat. Yep, all good. Cool. Awesome. Good. I yep. So thank you everyone for joining. I'll give it another minute or two and hope a few can jump on, but forgive me if there's any technology issue. I was freaking out about 3 minutes ago because I've never used this software before. It's meant to stream to LinkedIn as well, so I don't even know if that's working, but the fact that there's a few people here says enough, which means, we've had enough people work out how to get in. So good. Looks like we are rolling. Excuse me. All right. Sean, you're saying you can't hear anything? I guess, yep. I guess everyone, a few others say they can. It might be your end, Sean. But if anyone else is having troubles, let me know if you think it's my end. Otherwise, we'll get going pretty quickly. I know it's late for most people, and yeah, sure, your family's all waiting for you or whatnot tonight. So this will just be a relatively quick session. I will hang around and answer some questions at the end, but yeah, no obligation to stay on. But I hope you'll really get a lot out of it. So this is a topic, crane stability, which I guess is a pretty straightforward topic, some people might think, but then you realize not a lot of people understand it on a slightly deeper level. Now, tonight I'm going to try and this is aimed essentially at all levels of expertise. If you're sort of brand new and engineering and physics certainly aren't your thing, don't stress because I'm going to really simplify the principles. Or if you are an experienced engineer or operator, this is also for you as well because it might show you a different perspective to view cranes. So let's get moving a bit further. So first of all, I guess I should certainly introduce myself and Crane Class and what we do here at Crane Class. So at Crane Class, we're Australia's leading training provider for heavy lift activities on Tier 1 construction sites. So our goal is to empower construction professionals. So that includes anyone from site engineers through to supervisors and operators, and HSEs especially, with the skills to plan and execute heavy lifts safely and confidently. Now, we exist because of one main reason that I call the construction industry's biggest knowledge gap. Lifting operations are arguably one of the highest risk activities on your construction site. But most construction professionals have never been properly trained how to plan and execute lifts safely. And whilst planning and executing lifts might sort of be a step up, most people haven't been trained at the foundation level on simple facts of what are cranes and how do they work. And that's one of the things that we're trying to work on today. Now, very briefly, a little bit about myself for those of you who I haven't met before. But very briefly, my journey in cranes. So I started out at a small company at the time known as Advanced Cranes. Their biggest crane was a 160. And I essentially started there, was given an A3 bit of paper and was told, this is a lift plan and you need to work out how to make these. And essentially, that was my task. And I learnt a lot, failed a lot, and really, soaked up all I could in a smaller crane company there, getting out on the ground and seeing how things really work. And I certainly still advocate that some of the most challenging lifts are the small lifts you might do in backyards or side streets versus these bigger lifts over here, wind turbines and that. There's just the level of risk is almost a lot higher in the things that can go wrong. So certainly glad for that experience and learnt a lot there. after that, I jumped over to CPB Contractors on the Westgate Tunnel project. So that was one of the largest projects in Australia at the time, and we had an absolute plethora of cranes. I was in the East lifting team there, and was responsible for reviewing and approving lift plans, creating lift plans, but also compliance and safety on site and making sure that everything was being done as per standards, regulations, but also our internal policies, which are really important. Then after that, I was lucky enough to jump over to BMS Heavy Cranes. For those who haven't heard of BMS, top 5 global crane owning company and specialise in wind turbine erection. So a lot of onshore wind turbines in Australia with the LG 1750 that you see there, and then got involved with a little bit of stuff overseas with bigger cranes such as the LR 11350 as well, and also did a good scope on the Westgate Tunnel project working back for BMS, installing about 9,000 tonne of steel beams. So I've been lucky enough to see both sides of the fence and work alongside some really good people that have helped me gather the knowledge that has got me to where I am today. But you're all here for crane stability and to understand the basics of that. So let's dive straight into it. Let's have a look at a crane itself at its absolute core. Now, a crane, by dictionary definition, is a mechanical device used for moving heavy objects by suspending them from a projecting arm or a beam, relying on the principles of leverage and motion. Now, to understand cranes a little deeper, we actually want to go into understanding, well, how can cranes fail and what are the mechanisms in which they fail? So there's 2 main ways in which a crane will fail. The first is structural failure. So that's when any mechanical component will essentially rupture or break, be pushed past its limit. So here you see that this boom has essentially been bent because it was pushed past its structural limit. The other mode of failure is stability failure, and that is when essentially the crane tips over. Now, from a physics point of view, and what I'm going to go into explaining to you all is that essentially the overturning moment of lifting the load exceeds the returning moment of the crane and its counterweights, which mean that the combined COG of that whole system was out past the tipping point and the crane went over. Now, that's a very quick summary of what we're going to break down further tonight. So first, let's have a look at the basics of load moments. And let's just do a very quick exercise here. So here we've got a mobile crane, and let's just look at it in terms of we've got a line of outriggers at the front and a line of outriggers at the rear. So if we run an exercise here and say that this crane is lifting a load of 10 tonne out here, and that's at a distance of 10 metres from the tipping point. So we're saying that this outrigger is the tipping point or the tipping axis, the fulcrum in which this crane will pivot over. It'll rotate clockwise about that point if it were to go over. So the load moment out here is 10 tonne at a distance of 10 metres from the tipping point, which 10 times 10 gives us 100 tonne metres of overturning load moment. Now, then at the rear, we also have returning load moment. For the crane to not tip over forwards, the returning load moment needs to exceed the overturning moment to prevent that crane from tipping over. So if we've got 100 tonne metres at the front, that's the clockwise force pulling us over, we need at least that or greater to provide stability to the crane. So let's just say that the COG of the crane that's counterweights is back here, and let's say this is 5 metres behind the tipping point. We need at least 100 tonne metres, so we need 5 times something to equal 100. Well, that number, 100 divided by 5 equals 20. So what that's telling us is that if the combined weight of the crane and its counterweights weighs 20 tonne, and that centre of that mass is at 5 metres behind the tipping point, then we've got 100 ton meters of returning moment. Now, that would mean that the system is in balance and the crane is on its absolute limit of stability. It's about to go over. So ideally, and the way cranes work, is that we have extra returning moment to counteract the overturning moment. Now, I'm going to simplify this a little more right now. Okay, so what I've got here, I call this the rig, and this is a scale model rigging tool that I've got. Essentially what I've got here, I've set the rig up to be a symmetrical load, and I'm hanging it freely about the center points. What you can see is that the load is hanging level because the lift points are above the center of gravity. Now, let's clarify right now what the center of gravity actually is. So the center of gravity, excuse me, is the point in a crane or a load where the total weight is considered to act. What that means is if you could balance the crane or the load on just one point, it would stay level. So right now we're hanging it above the point, pardon me, but if we were to support it beneath that point, it would balance about that point. And that's the basic concept of center of gravity. Now, for crane stability, the crane will remain upright only while this point stays within the base of support formed by its outriggers or tracks. And we'll come a bit further into that. But let's just actually use this to clarify the basics of load moments. So what I've done is I've added one plate to one end of the rig. And let's just say, to keep it simple, that that's at a distance of 2 meters. Now, what that's done is shifted the center of gravity of this system slightly towards the heavier end. Now, because we're hanging the load above that central point, that center of gravity wants to come beneath the point where it's hanging. So the load actually tilts and rotates to let that COG come back in, and we now have the load on a new angle. Now, if I then go and add 2 plates at a distance of 1 meter on the other side of the COG, we've essentially got our overturning moment of 1 plate times 2 meters. So we can say that this is 2. We could even just say it's 2 ton meters. We could say it's 1 ton at 2 meters. So we've got 2 ton meters. And then what we've also got is 2 plates at a distance of 1 meter at the rear, the returning moment, which also equals 2 ton meters. So whilst we've got 2 plates at half the distance or 1 plate at twice the distance, both either side of the support point, this load is now level because those load moments have balanced themselves out. All right, we're going to step this up a bit now and take this a little bit further. So what I've done is I've used this rig, this frame, to simulate a crane on outriggers. The first scenario, so this black line is a table. This load was sitting on a table, and we're using these support points as outriggers. So let's call this the front outriggers and this the rear outriggers. What I also did was set up a spreadsheet and a graph, you could call it, that actually calculates the COG and the loads based on how I change the load. We're going to use this to describe stability, and then we'll take it to the point of adding the safety factor in that's built into cranes, because that's what we're going to get to tonight, to really understanding those safety factors. And you'll see what load tips this crane versus what load it would be allowed to lift on if it was designed, say, to EN 13,000. So right now, we've got this load, center of gravity, central between the front and rear outriggers. The frame right now weighs 3.43 kilograms. You can see that the reactions on the front and rear outriggers are equal. We've got no load on the front or the rear. So what I then went ahead and did was added load to the front of the crane, you can say. This is 5 plates at a distance of 205 millimeters from the front tipping point. The theory tells us that what that has done is shifted the center of gravity, the combined center of mass of this whole system, to a point that's 2 millimeters inside the line of these front outriggers. And the crane was still stable there because that COG is inside the stability region, being the area between the front and rear outriggers. I then went ahead and added a 6 plate. What that's done is failed the crane. The crane has failed in stability and tipped over. And the maths tells us the same, that COG is now 6 millimeters past the front outriggers, which means the crane itself tipped over. Now we'll come back to that, but let's actually tie this back to a real crane right now. So what we've got, this is a Liebherr 250-ton mobile crane, and I've simulated this in Crane Planner, their lift planning software. Right now, this crane's set up with full counterweight, and it's jibbed all the way up to minimum radius, boom sucked in, hook weight only. Crane Planner gives us the COG of the crane. And you can see in this situation right now, it's actually pretty much right in plane with the counterweight, because that is, what's the word I was looking for? Contributing, that's the word, contributing the most to the overall mass of the crane. And basically, you can see that it's all the way towards, really this is the front outriggers, but I'm just going to call it the rear outriggers. And that's just a key point, completely off topic, but that's why no load min radius in lift planning is often one of your most critical scenarios. When you don't have a load on the hook, you've got all your weight at the rear, and that's where you're at risk of going over backwards. But if we then go and add a load onto the hook of this crane, so I've poked some boom out, I've added some load, and I've pushed this crane to 100% utilization. What this has done is pushed that combined center of gravity of the system towards these rear outriggers now. Now, you can see here that the center of gravity, it's still not on top of the rear outriggers, which would mean the crane is still not close to tipping. But this is the limit that the computer is letting us go to. So the question you should be asking is why? Why is that? The answer is safety factors. And it's due to the safety factors that are built into the crane to prevent cranes being pushed to their absolute limit. So let's have a look at those now. Now, tonight I'm just trying to give a basic overview of this. You could dive a lot further into this, but to put it simply, in Australia, our mobile cranes are designed to AS 1418 Part 5, which is a modified adoption of EN 13000. And in EN 13000, that's the European standard, and that refers to the ISO standard, the International Standard 4305, to provide the safety factors for the design of mobile and crawler cranes. Now, you don't even need to remember all of those. Just know that we refer to an international standard in Australia to provide the safety factors for our cranes. Now, this is pretty simplified, but most cranes lifting from a stationary position will utilize what's known as the 75% chart. So that means that the load chart that's programmed into the crane will show 100% utilization when the crane is at 75% of its tipping capacity, the point in which it would fail in stability. Okay, so to reiterate that, if it would take 100 ton to tip a crane over, the computer only lets the crane lift 75 ton in that scenario. Now, if we do some quick maths, 75 times 1.33 equals 100. So what that tells us is that there's a 33% safety factor built into cranes that are using the 75% chart. Now, that might sound like a lot, but in reality it's not. And we still see cranes go over quite often. And we'll tie that back in at the end on why it's really important to understand what that safety factor is there to allow for. But at this point, just understand what this 75% chart is. Now, there's also a 66% chart. Look, if I could have people talk, I'd be asking why people think we have a greater safety factor here. The 66% chart is used in pick and carry scenarios. It provides a greater safety factor to account for dynamic influences when the crane is traveling. So you see here, this is off a TID, which is another variant of an articulated pick and carry crane, otherwise known as Franners, another variant. And when that crane is pick and carrying, it uses the 66% chart. 66 times 1.5, or 66.6 times 1.5 equals 100. So this hence provides a 50% safety factor to the tipping limit of the crane. And that might seem like a lot, but once again, we still see these cranes go over. So it is verified and there for a reason, and we will come back to that later on. And that's exactly what's showing here, that this crane is only pushing to 75% of the point where it would tip over. Now, what I've done next is I've actually gone and programmed the safety factor into our scale crane, our model crane, you can call it. So we've seen here that at 6 plates, the crane was tipping over. What we want to do is work out what our capacity is. So what mass out on this point will actually tip the crane over. Now, all right, I'll take that forward here just to show. Okay, what I worked out is that 860 grams is the limit that will tip the crane over. So our capacity now, our tipping capacity is 860 grams. But if we take that out, take that back, don't worry too much about all these numbers here from my spreadsheet. But I guess what you can see is that we've got 825 grams on the hook, which is these 5 plates. And you can see, like, our reactions, we've only got 70 grams or 7 grams on the rear outriggers, and we've got 4.18 kilos on the front. This crane is very close to tipping. And then we've put a formula in here, which is the current load being 825 grams divided by the load required to tip it, which is 860 grams. So as a percentage of our tipping capacity, we're now at 96%. But what we want to do is then add in the safety factor. So underneath, I've then put that tipping load times 0.75 to show what percentage of utilization we are actually at on the 75% chart. If I go a step further, hopefully this will bring it home for a few of you. So I've added a little bit more weight. I've taken it up to 860 grams. We're now at 100% of the capacity in which it would take to tip. 1 more gram and this crane would tip over. But we're at 133% of chart utilization. Okay, so look right here. So I've got 860 grams. I've then wound that back to 645 grams. What that's done is taken us back to 100% utilization of the load chart. And at that point, we're at 75% of the tipping capacity of the crane. This right here is exactly what we were seeing back then. This is how cranes work in real life. There's a few other tiny factors that come into it, but this is the overall basis of crane stability. So you see right now, this crane at 100% capacity can lift 645 grams, although it will take 860 grams to tip the crane over. And this is that 33% safety factor that's built into the crane. Now, what we can also do is program the 66% chart into this as well. So you see before, so I've gone back up to that tipping load of 860 kilograms. And you see now, whilst we're at 100% of the tipping limit, we're at 150% utilization of the load chart. So to wind this back to 100%, we've now had to drop the load down to 565 grams. Now, so let's bring that back. It takes 860 grams to tip the crane. If we're standing still, we can lift 645 grams. And if we're pick and carrying, we're dropped down to 565 grams. This is exactly the scenario of if you were in a fronter and you picked a load stationary off a truck, you'd be able to lift up to, let's just call this 6.45 tonne. Let's say you could lift that stationary off a truck. If you then want to pick and carry with that load, well, you can only lift 5.65 tonne in that configuration. So you'd need to probably reduce your radius, suck your boom in to get the extra capacity. But what we've simulated is that it would take 8.6 tonne to actually tip that crane in a controlled environment where there's very little other risks that can go wrong. And that's what we're going to come to in a second, because that might seem like a lot, but these safety factors are here for a reason. And that's where we come to right here, that have you ever heard an operator or someone state jokingly that the crane has extra capacity up its sleeve? This is likely where they're coming from, but it's likely without a deeper understanding of why it is necessary. And this is why. The margin that's built into cranes is not spare capacity. That margin is already being consumed by real-world effects. And that's why we see incidents like this occurring, well, worldwide daily, but even in Australia, you nearly see a crane accident at least once a week, if not every couple of weeks. The spare, well, it's not spare capacity. The margin, the safety factor, is being consumed by things such as wind. The crane needs to be able to take additional wind loading. Dynamics. Now, that can be when you're pick and carrying, but it can also be dynamics of a load. So just that load bouncing around when you come off the controls, or when you come up and down, or the inertia from a halting movement. So even if you're slewing and come to a stop, no matter how slow that is, there's going to be some dynamics from that inertia into the crane. And the point is that these often act together, and that's why that safety factor might seem so significant. But when they do act together, that's when things go wrong. And that's why cranes have these safety factors built into them. The only reason a crane stays upright is because the chart is already pulled back from that tipping point. Understanding these principles should never encourage recklessness, but should enforce discipline. And just finally, the rated capacity chart is the operational limit for a reason. Now, one more thing there too, and on safety factors are a basic engineering principle. They're not just present in cranes, and they're present in all machines and structures. Even our rigging equipment, for example, our chains, a 4-to-1 safety factor, slings a 7-to-1 safety factor, which means you could put 7 times the limit that a sling is designed to before it will failure. And that's because there's greater risk involved with those devices than in the crane. So the crane can only be pushed an extra 33%. A sling shouldn't fail until 700%. safety factors are in everything. And as you see right here, things do go wrong when we work too close to the limit. So safety factors must be respected. Now, where to from here? That's pretty much the summary I've got of stability. If you want to have a look further into this, these are some of the standards that you can, of course, read up on. Now, I will come back and have a look at the comments in a moment. If you do have 2 minutes to allow me to introduce our new offering that's about to come out at Crane Class, I'd really appreciate that. And there's some bonuses here for anyone who is going to jump on the wait list for that. I'll present this very quickly. It's our new level 1 Crane Fundamentals. It's available from 29th September. And this is aimed at the absolutely fundamental level of anyone in construction who deals with cranes, deals with basics, sizing up a lift, understanding mobile cranes, safety essentials, so your certificates, your qualifications, basics of rigging, and then some industry-specific electives. You can scan this QR code and jump onto that page and have a look. Otherwise, I will send you a link to that page. Otherwise, I know it was short, I know it was sharp and brief, but that's pretty much it that I had to discuss today, guys. I am jumping over right now to just have a look at the comments. If anyone has some questions on what we just discussed, happy to take the time and go back through it. And you should be getting a recording tomorrow if the technology works properly. So I'll be trying to do that very shortly. But hang around for the questions. Otherwise, feel free to enjoy the rest of your night, and thank you very much for tuning in. James, I see is lift designer course still in the works. So yes, we're breaking the course up into level 1 and level 2. So level 1, I've just shown you, crane fundamentals. Level 2 is the lift specialist course. And that's going to take everything a step further and, really deep dive to a deeper level. But the level 1 is a prerequisite as well, because we find that even experienced operators who do the core basics are really glad that they did it, because they always pick some things up. Thank you very much for all the comments, everyone. Any other questions? Cal, what do you got here? It's dynamic wind loading change for each lift plan, i.e. dependent boom height. Obviously, wind loading higher at boom, 50 metres versus 10, yes. And lever O, easier to assess for ultimate/service loads in overturning moment, additional to low capacity. What is the safety factor on counterweight? That's a solid question there, Cal. I'm debating where I start. So I'm just reading the other questions too. Scotty, will the notes from this short course be available? I won't have the notes from this available, Scotty, but you should actually get the replay recording. So that'll be even better. You can go back and watch any bits that you'd like. Let's just, for the first part of yours, Cal, so the dynamic, the wind loading on a crane is assessed as part of each plan. So with wind, cranes are designed with a chart wind speed, and that chart is based on a area to mass ratio, and that's 1.2 meters squared per ton. That gives the chart wind speed that the operator will see on their screen. But it's up to us as lift planners to then determine if the load is within this ratio or exceeds it. When the load exceeds it, then there's a formula that we use to reduce that allowable wind speed below the chart wind speed to stay safe. So essentially, cranes are designed for specific wind speeds take into account the area to mass ratio, and then we reduce accordingly from there. Yeah, Nick, I think you got a good point that wind 100% is a full session in itself. I'll put that in the diary for later on. Certainly one that we could do. Tom, is there any instance where a crawler crane can move with a load, meaning roll on the tracks with a load? 100% there is. There's a few things to take into account there, Tom. So one is regarding the crane itself. So some cranes will allow you to do it very slow with no deration from the stationary chart, whereas most cranes will require a deration from the stationary chart to do so. So I guess the first thing is the capacity of the crane, and does it have the capacity and capability to do so? The second is then, of course, the dynamic loads that what you're more worried about is the loads that are imposed on the ground. So that loading is going to be amplified due to the dynamics. And even, if you're lifting precast concrete doing this, you need to consider that the anchors have been designed for dynamic loading as well, because you're going to put additional loading on the load and everything else. But 100% that's possible. If you're going to pick and carry with a crawler crane, best practice is actually to pick the load and then you jib up, so boom up, shorten the radius to a position where the crane's actually relatively balanced. Bring that COG central about the track so that it tracks a lot nicer, and then jib down when you get to your place scenario. For barge works, are these load charts for barge works? Are these standard with cranes info, or do you have to ask manufacturer for them? That's a good point, Scotty. And I probably should have touched on the point about the cranes are designed to be used on flat ground, to put simply, and each crane has various levels of degrees, typically 0.5%. But when we're on barges, then we're obviously on a floating structure which can see greater tilt or list, as it's known. Some cranes are more friendly with this scenario, you could say. So like your Manitowocks typically will provide barge charts, and even your Nenzing model levers, like your LR 1300, that sort of thing, typically will provide charts for you and will be more friendly to listing in barge scenarios. But a lot of other cranes, if you're going to put an LR 1350 or an LR 1750 on a barge, you'd be going to lever for reduced capacity charts for a greater angle. Do you run a course that doesn't need the attendee to understand load moments, etc.? Stu, great question. And that's what the new Crane Fundamentals course is focused on. We do touch on very briefly this same topic that I've just discussed, but understanding load moments, of course, aren't a key requirement. I do find, just if I can explain in really simple terms, it just helps understand cranes a bit better. But to answer your question, this course, the Level 1 Crane Fundamentals course, which is out at the end of September, is aimed at the absolute fundamental level that anyone in the crane industry or in construction should be able to follow along with and keep up. All right. Seems like I think I've got through most of the questions there, guys. If there's any other questions, otherwise I'll let everyone get on with their night. All right. Let's do that. Really appreciate everyone jumping on. I will look to run another one of these in a couple of weeks' time. You'll certainly see that on LinkedIn, or I'll shoot an email out about it. But yeah, and if anyone's got questions on today or wants to know more about what we do, feel free to reach out. Look forward to hearing from you all. And yeah, thanks for joining. Have a great night.